Hi guys. Today we're doing the educational round as I promised, round 101. I'll quickly update the sub count and then we'll get into things. Now this round's gonna be fun. I can tell I'm getting a bit sick, which means things are gonna be interesting. And also we're gonna be trying out this writing tablet again. See how this works. I imagine it's going to be terrible. So let's see. A bracket sequence is called regular if it is possible to obtain a correct arithmetic expression by inserting characters plus and 1. You're given a sequence S. There's exactly one character of that and one character of that. Okay, so first the length of the string has to be even, and then this is gonna go so badly because I can't even I don't even know how to draw with this. Okay, let's see. So this works, right? So say we have a sequence like, for example, like something on the end and then maybe some question marks and stuff like that. So if we have these things on the end, then it's going to be impossible because there's nothing we can do to balance this character out, and the same for here. So if we have either of these on the end, then it's not possible. Otherwise, it should always be possible as long as the length of the string is even, because if the length of the string isn't even, we can't do anything because it won't ever be balanced. But otherwise, I think we can just allot the first we have a string of length n minus, or 2 of the characters are taken already, so we have m minus 2 over 2 left. So we can make this many of these and this many of these at the same time. And I think that should work. So let's see. We have test cases. If S0 is equal to this, or S dot length minus 1 is equal to the bad character, then it's also impossible. And let's see, otherwise, let's see. And just go through and replace the characters. So if SI is equal to a question mark, then replace it with something. Oh, actually, we don't even need to do that. Okay. And the reason it's always possible otherwise is because we can always do something to counteract these things. We can always do something to counteract these things on the end. For example, as long as we have a question mark before the right-facing parens and a question mark after the left-facing parens, it doesn't matter what else happens. We can turn this into a left-facing parens and turn that into a right-facing parens. Okay. Imagine that should work. Yes, no, yes, yes, no. Okay. Totally sabotaging my speed here, but that's okay. It's not really that big a deal. Speed is not my concern. Open the rest of the problems now. Assume we got that passed. Okay. Let's see. Try and erase with this too. Why not? Alright, you have a sequence A consisting of A, n plus m integers. Painted the sequence into 2 colors, red and blue. N were red, the other ones were blue. After painting the elements, he took the sequences of the red elements and the blue elements, and he only has the sequences R and blue. Oh, the values? Wants to maximize the prefix sums. Okay, the annoying part is that they could be equal, because then you have to like figure out how to decide things. Actually, how would this work? It's not like graphically, it's like different. I guess it's like which elements to make red. Hmm. Which elements to make red? I'm not sure if that helps. The idea would be something like taking these sequence into account. Like for something like this, a certain element here, for example, this 3 would contribute to all of these prefix sums. Oh wait, is it? Wait. It's the maximum of the prefix sums? Maximum of the prefix sums and 0. Why does 0 matter? Anyway, we can just, I guess we maximize the prefix sums by the maximum value of a prefix sum. Which means it's going to consist of some prefix of the red values and some prefix of the blue values. I guess we can just like... Okay, wait, yeah, I kind of misread this. That's fine though. Let's see. So it's going to take longer to draw this out than to actually do the solution, but like... The idea is if these are the red values, let's just imagine these are red and the other ones are blue values, then when we're considering some prefix sum of the whole sequence, it's going to have some of the first few red values and some of the first few blue values. And the idea is that, like, if we have this red value, because the sequence is like in order, we have to also have all the previous red values. So no matter what, we're going to have some prefix of the red values and some prefix of the blue values, and we want to find the maximum way we can pick some prefix of red and some prefix of blue. And so the way to do that would be to just like, I think just check the sums of all of the prefixes or all of the pairs of prefixes. Like try all of these and try all of these corresponding ones. And then take the best of those. That would be my guess. Can I code in this? That's interesting. Okay. C into N to M. I would imagine. Oh. C into N. I do see that typo. Okay, so R equals 0. R plus equals AI. It's R2 plus equals BJ equals max. It's, why don't I just make this? No, actually, it doesn't make sense. R plus 2. So we're just trying all of the prefixes because we know the answer must be of that form anyway. Are there multiple tests just with that? Or wait, never mind. It's just a single test. So N, M, AI, BI. Try the empty prefixes also. So we consider 0 first. And we consider having this, taking no blue elements, and then taking some of the blue elements. Yeah, looks good. Oh, or not? Okay. What have I messed up this time? What am I doing then? So we start off with 0 because it's the beginning value. Then we consider taking no elements in the red sequence. Then we take 1, then we take 2, we take 3, and so on. What have I messed up? Is there something between test cases or something? I'm not sure what I've done. I don't know what's going on. I mean, I mentioned it's not the problem between test cases, yeah. Well, I don't know. I'm considering, oh wait. Oh wait, I'm not considering only the blue ones, okay. I forgot to do that. Alright, yeah, that makes sense. So that would, for example, fail for something like 1. Somehow I thought I was handling that case, although I'm clearly not. So like without that, the answer will be 4. Yeah. I'm sure it still passes samples. Alright, that was dumb. But okay. I'm going to build a fence that will consist of n equals sections. All sections have a width equal to 1 and height equal to k. Place sections in one line side by side. The ground is not flat. Consecutive sections have a common side of length at least 1. First and the last sections should stand on the corresponding ground levels. Sections between maybe either on the ground level or higher, but not higher than k minus 1 in the ground level. Is it possible to build a fence that meets all rules? But not higher than k minus 1. So let's see, if we have some fences that are too far apart, then it's not possible. What classifies as too far apart? I guess what we can do is we can try and draw again. I guess what we can do is we can try to, so we have this ground level. For example, like this, right? That's what they have. And then keep pressing this button that ends up canceling the whole stroke, and that's kind of sad. It's like that. So I guess what we can do is we can start by, we can maintain like an interval of where this, like for example, this tower could be. What is that not? Oh, wait, I can't. I'm trying to draw on this and it's not working. Like we can maintain an interval of, for example, where this tower could be. Like in the beginning, it has to be on the ground level. So there's only like one spot it can be. In the second place, it can be anywhere from here to here, as long as we make sure that we satisfy the constraints. Like for example, somewhere there. This being the place at the bottom. And then here, the bottom can be essentially anywhere from here to here, I believe. And then this depends on both its own constraints and the constraints of the previous one. And we're sort of like intersecting a bunch of intervals. And I believe that would work. And then at the end, we see if we have a non-degenerate interval or something. Let's see. Let's not make the mistake of reading in only half of the input and breaking. So alright, now let's see. I'm going to write intersection between intervals. And the way to do this is to say we have two intervals here. Then we could have something like this, and then something like this. And the intersection is the maximum of the two starting coordinates and the minimum of the two ending coordinates, because this interval is the intersection between them. And if the intervals don't intersect, then the maximum of the two and the minimum of the two will form a non-existent interval, which is what we want. So it's just taking the maximum of the starting coordinates, max a dot first, and the minimum of the ending coordinates. So from the end, then we have special rules. If I is equal to 0, and the only height we can have is our initial one. Otherwise, we can go anywhere from our initial height to that plus k minus 1. Yeah. Plus k minus 1. And then from there, now we want to figure out, since this interval we have is kind of constrained based on the previous one. Like, for example, here we have this range. And here we have this range for placing the interval based on the constraints of this height. We also have the constraint that it has to like match with the previous interval. And the only way to do that is to make it so the bottom of like whatever block we take, it has to match with this. Meaning that its height plus k minus 1 or something must be the same as, like, it must coincide with this. And so the way to do that, one thing we can do is we can simply like extend this interval down by k minus 1. So that this interval can actually start here. And then we can take the intersection of these two, because then this intersection would be the possible intervals such that it's both within the red range and it's tall enough to reach the blue one. Yeah, that would essentially be how that works. And then we don't extend this, because then this would be based off the bottom of this one. Actually, maybe we would extend it. Actually, yeah, I think we would extend, I think we would extend this one up too, because then that corresponds to the cases where this one is tall enough, where like this one's higher, but this one's still tall enough to reach the other one. So, cur dot first minus equals k minus 1. Cur equals isect cur pause. Wait. I should call this something other than, actually I can call this ants, yeah. Ants equals 0. Break, because we don't care what happens then. Now actually the question is, do we want k minus 1 or do we want k? Well, we want k minus 1 actually, because the intersection needs to be non-empty. So yeah, let's see. Works for that. It's not trustworthy though. So let's make sure we're satisfying all the constraints. The consecutive sections should have a common side of length at least 1. Yep, that's how we do this. Because again, we're extending these by k minus 1 down and up, so that this represents the range where the intervals would intersect. So actually, I can draw this too. So this is like up k minus 1. And it's k minus 1 and not k, because again, they have to like have a non-zero intersection. So let's see, the first and the last sections to stay on the corresponding ground levels. Yep. And they may be on the ground levels of higher, but not k minus 1 higher. And that's what this is. Okay, and this is just randomness. Yeah. It's a random huge interval. Let's see. Okay. Imagine we're not doing that good. I'm kind of tired and slow right now, but it's fine. It's not really about that. So you have an array A where AI is equal to I. Oh, fun. In one step, you can choose two indices x and y and set AX to the ceiling division of that. you want to make array A consist of m minus 1 ones and 1 2 and no more than m minus 5 steps. Note that you don't have to or m plus 5 steps. Note that you don't have to minimize the number of steps. So we have something like, that's satisfying to do. Okay, so we have something like this. Like 1, 2, 3, 4, and 5, for example. In one move, we can pick some integer, pick some other integer, and set this integer to the ceiling division of that by some other integer. For example, then this would become 2. Now let's see. And we have n plus 5 moves. We want to have 1, 2, and the rest of them should be 1s. Okay. So if we divide this by this, for example, and we get, this becomes 2. So we can get a lot of 2s by doing this. Let's see. We do something. What else? If we do this by this, then we get 1. When we have a 1, there's nothing more we can do with it. So 1s are totally useless to us. Which means like the biggest element is kind of the problem. We want to kill that somehow. How do we kill the biggest element? N plus 5 is so small. So yeah, dividing anything by the biggest number will make it so it works like that. The problem is, how do we handle the biggest number? Again, having some sort of we don't have a log. It's just that 5 is so weird. Like 5 isn't log, so that doesn't work. I don't know what that would require. So n minus 1 ones and 1 2. Right. Let's throw in a 6 just for fun. Just make it easier somehow. Problem is, the bigger numbers we have, the harder it gets, I would suppose. It's like, what kind of power do we have with our operations? So when we divide some number by some number smaller than it, we get at least 2. Because ceiling. When we divide some number by some number bigger than it, no matter what, we get 1. Bigger than or equal to. But when would it ever be equal to? If we do some square root thing, wait, how does this work? What's the square root of that? How long does this take to converge? Is this what we need? Is that what we need to do? That seems so close. I mean, it is 5. It is 5, that's true. So we will end up below 2 eventually. So the idea is like, pick some number k or something. Then divide like everything by the biggest number until you get to the point k. So like kill these, make them 1 by dividing them with 6. And then now we divide 6 by this number so that this number is still greater than everything else. And then we continue. I mean, this is something we can test, I guess. Oh, but also we save an operation on the first element, I suppose, so maybe it's better. I'm going to make this a separate function so I can test it on my own. So let's see. Okay, so my actual idea is to sort of like, so we pick some number k. Let's set k equals 3, for example. And then actually k equals 2 would be better. And then we kill everything between k and 6, or the biggest number. And then we divide this. We divide this 6 by k or we divide the largest number by k so that we get a number that's still the largest, but it's like as small as it can be while still being the largest. And the optimal choice for k would be like, oh, square root n or something. And then we do it again and we keep going until we get to 1 or something. Actually, when we get to this 2, this would be when we stop and we start killing this element. And I guess the idea is that with square roots, it converges very quickly. Like, for example, with this, it would take 5 square roots to get to 1.4. Although I don't really know. Okay. Let's do, just for convenience, void up. J. So we set AI is equal to AI plus, this is just ceiling trick. N minus 2. So let me say, if a m minus 1, if the last element, if doing the operation on the last element, let's see, if doing the operation on the last element will still make it bigger than this number, then this is our choice of k. So plus AI minus 1 over AI, or is greater than or equal to AI, then op I m minus 1. Yeah. And then while a m minus 1 is greater than 1, op. Because then we use this 2 in the end to get rid of this. This is sketchy. And it doesn't work. Oh, because it should be the other way around. N minus 1, 1. I reversed all of these. Yeah. Okay, right. So don't want to do that. Well, it is the same operations they have, although I'm not sure if it'll work for bigger ones. So 50. No. 50 uses 51. 1. That would not have a chance of working. Okay. $100,003, $500,002, $100,002. Okay, so it uses that most m plus 3. Let's also make sure it actually does the operations right. 1,500. Okay, looks good, I suppose. And just review the code to be safe. So initialize the values. If it's like a good number, do the operation with that, then do the operation with that. And the reason this doesn't take that many operations is because k is O of square root n. Because like dividing, like the number that you divide by to make it greater is going to be on the order of square root n. So it's like n over k is greater than k or so, and then it's like n is greater than k squared or something. Like that's where the square root comes from. So then like doing it multiple times is basically like doing iterated square roots, and this is going to converge very quickly as I've tested here. So that's the idea basically. And I guess it also saves a couple operations because you don't use the first element, you never use the second element. It should be good. Okay. Indeed looks good. Alright, we get a bit problem. Great. Let's call it a string problem and a bit string problem. Let's call two strings A and B, both of length K, a bit similar, if they have the same character in some position. There exists at least one I, such that AI is equal to BI. You have a binary string S of length N, an integer K. An integer K. Let's denote the string S I to J as the substring of S starting from the ith character and ending with the jth character. Yeah. Let's call binary string T of length K beautiful if it's a bit similar to all substrings of S. Having length exactly K. Goal is to find the lexicographically smallest string T that is beautiful or report that no such string exists. String X is lexicographically, yeah, okay. So you have a bunch of test cases, each one has N and K, and that's it. Exactly in uppercase, okay. Interesting. Interesting that they write that checker that one. Okay, for the possibility condition, there's something going on like for the possibility condition, there's something going on like say k equals 3, and then you have something like a lot of ones in a row. And like the only thing you could ever do is just to have a string that consists of all ones. Because if you have, like say you have a lot of ones, then you can't have too many zeros, for example. You can't have a string of all zeros, otherwise you'll never be able to satisfy this. But if you have a run of at least k ones, and say you also have a ton of zeros, you have at least k zeros, then no strings ever. Or actually, wait, is it the no string will work? No, I don't think so. Actually, no. There should still be some strings that work with this. Okay, never mind. That's stupid. K plus 3. Right. So that's not very helpful. It's something like we start with a string of all zeros, and then like we start with a string of all zeros, and we want to do something like binary search or something on the the largest possible character that works. How would this work? It has to always be possible, because if n's or not always possible, but it has to be possible pretty often. Yeah, I think what they do with this test case is they enumerate all possible bit strings of length 3, so that no matter what, there's something that won't work. And you can do that with small k, but with large enough k, it's just not going to work that way. That's not going to be possible to do. Let's see, is this some sort of string algorithm bash? I don't know. I don't want it to be that. That would be not fun. Let's see, how are we doing? Okay, not that fast. Not that terrible, but not that fast. Beating second thread somehow. Maybe he's having a worse day than I am. Who knows? How'd I screw up B again? Oh, right, that was the not considering the empty red sequence. Okay. So two strings A and B are bit similar if they have the same character in some position. Right. something else that could be interesting. Because it's binary, like, consider the string 0, 1, 0, for example. Like, either, basically, like, consider the exact complement of the string. That is, like, every bit is different. 1, 0, 1, right? So every other string, if it's not equal to this string, then it must have one bit, at least one bit that's different. Otherwise, it would be equal. And therefore, because it's binary, that different bit is going to be equal to the corresponding string. So every string that's not the complement is going to be a bit similar. Which means that, like, there aren't that many characters to check. Like, I mean, every substring of length k is going to block out its complement and only its complement. So that means, like, at most, O of n minus k strings are going to be blocked out. And so I think with something like hashing, we can just straight up try all the possible strings, or as many as necessary, until we get something that works. I think that's just it. I think that should just work. Now, the problem is this is an edgy round, and so hashing is going to be hard. So maybe there's, like, a better way to do this. We can't do something like a try. That's too hard. Maybe it's some sort of suffix array magic, but I don't want to do that because I don't know how that works, or suffix tree magic. I'm pretty sure that's a solution to it. I just don't want to do that. So, I mean, we could do hashing. That's a possibility. Has nobody solved this? Wow. Okay. Hashing should work. We just need to make it randomized. Let me see. I just want to make sure. I just want to think about it and make sure this is actually going to not be hacked. Maybe it's even easier than that, actually. I think we only care about the last few characters. Yeah, because again, at most O of m minus k things are going to be blocked out, right? And n is 10 to the 6th. So that means, like, the best string is going to differ by at most only, like, let's say, like, 23 bits, for example. Which is going to be totally fine to deal with. Because 2 to the 23rd is like 8 times 10 to the 6th, like 8 million or something. So that's fine. So if we consider only the last 23 characters, then no matter what, we're going to have a match. So that's even better. Then we don't even need hashing. It's just integers. Yeah. Test cases is a problem, isn't it? Actually, no, it's not, because we can use timestamps. That's fine. Int ts. That's fine. I'm gonna implement this first because this is actually my chance to like do well. After all this stupidity of the weird like mistakes and the explaining and stuff, this should be good. So size equals min k23. Which I can make this long still, right? Because it's not that much memory. All right, 9 million times 8. Yeah, it's fine. What? We've so much memory here. Why did I plug that into a calculator? Okay, so let's see. I plus k minus 1 is less than n. I plus plus. This is the beginning to the end of the interval. J equals 0. J is less than size. J plus plus. If s. So it should be like I plus k minus 1, which is the end of this current interval, minus j. That is the jth last character, is equal to 1. R plus equals 2 to the j. Yeah, so it's fine. TSR is equal to. Actually, I don't even need nearly this many. Yeah, this is fine. TSR is equal to TC. That is, I'm using timestamps to make it so we don't have to reset the array every test case. It's like a visited array, except I'm marking it with the test case, so that if it's lower, then we know it's not visited. It hasn't been visited during this test case, which is what we're interested in. Now, I is less than 1LL size plus 3 or something. Actually, it should be 2 to the size. If TSI is not equal to test case, not equal to the current test case, then we're good. J is less than, how would this work? J is less than k minus size, J plus plus. Then everything's a 0. J equals 0, J is less than size, J plus plus. If this bit is set, which means I and 2 to the size minus j minus 1. Otherwise, we have not found a match. Okay. All right, actually, this should be 0 because complement blocks out its complement. 0 0 0 1 0 1 0 1 no. 0 1 0 1 0. And decay. Right. So again, we're looking through every substring, making sure it's within the bounds. Then we check, we construct the number from the complement of the string. Mark it as visited. Let me go through all the possibilities. If we find something, we just print it in binary. Okay. Yeah. Our answer in test 1. What? Did I not find an answer for that? Oh, what have I done? Wait. Oh, cause okay, whoops. Cause I didn't. Yeah, whoops. TSI is equal to -1 because we start with these test cases indexed at 0, which is fine. I just messed that up and didn't realize that I wasn't doing that. So yeah, 1 1 0 0 0 1 0 1 0 1. Okay. This is big enough, right? Yeah, it should be. Because we're only really interested in up to 1 million anyway. I'm just being safe. Okay, cool. No hashing done. And we're in 33rd. That's pretty cool. Interesting. Wrong is he must be using hashing. There's no other way. Yeah, that must be hashing. Because hashing is the only thing that's slow enough to like not work for this. Let's see. Okay, so this is pretty good. Would be faster if not for everything, but that's fine. This is still pretty good. We decided to drop the legend about the power sockets, but feel free to come up with your own. Okay. How many people solve this? Is this some sort of like data structure bash? Oh, it's a tree thing. Okay. Define a chain. A chain of length 1 is a single vertex. A chain of length x is a chain of length x minus 1 with a new vertex connected to the end of it with a single edge. To the end of it. So is it like a vertical chain, or is it chain of length x is a chain of length x minus 1 with a new vertex connected to the end of it with a single edge? What is the end? What's the end? I'm guessing they mean vertical chain. No, it's not. Okay, it's not. It's just a path? Like they say you have to have a path of length n or something? You're allowed to not use all the chains, so it's optimal to use only chain of length 4. Okay, what? So you're given n chains of certain lengths. Wait, so they just like inductively define a path. Alright. Each vertex of the tree is either white or black. The tree initially only has a white root vertex. All chains initially consist of only white vertices. What the hell? All chains initially consist only of white vertices. Also, wait, what's my runtime? It's good, right? Yeah, 93 milliseconds. Okay, we're totally safe. And the only reason I'm doing this weird thing is because we have multi-tests. Yeah, that's the only reason. Just because, like, I want to have a visit array across all multi-tests, but the thing is, it's O of 2 to the k. And so that's a problem because there's, like if I have k equals, nope, not what I meant to do. If I have k equals 20 for all test cases, then I have 2 to the 20 per test case, which means I have to do this many resets of the visit array. And I would have, like, 500 times 2 to the 20, which is, like, it's gonna pass, but it's, like, gonna be way closer than I want, so it's just not worth it. And the easier thing to do is just to have this, like, resettable thing. Yeah. And so this makes it so I don't have to reset. I use a timestamp array, which basically says if it's been visited in this test case, consider it, otherwise don't. And so this means, has it been visited in maybe some other test case, but not specifically this one? Anyway, that's a cool trick I like to use. It's more implementation side than anything. Okay, I have not finished reading this problem, so let's do that. Each vertex of the tree is either white or black. The tree initially only has a white root vertex. All chains initially consist only of white vertices. you can take one of the chains and connect any of its vertices to any white vertex of the tree with an edge. The chain becomes part of the tree. Both endpoints of this edge become black. So you start off with what? There's at least k white vertices in the resulting tree, and the value of the tree is the distance between the root and the kth closest white vertex. What? Okay. Distance between two vertices. The tree is the number of edges and the shortest path between them. Alright, so you can take any one of the chains. Alright, let me try and illustrate this, I guess. That's not what I meant to do. Alright, actually, let me do the satisfying. Oh yeah, okay. So, you can take any one of the chains, and we can attach. Wait, okay. So we have like this root that's white. I'll use red as white and blue as black. Sure. Okay. So we have, because I don't like drawing white on white is just not gonna work. So we have some stuff going on. So we have like a lot of chains just like floating in space. So for example, we can consider the second sample. So we have 4, we have 3, and we have 3. This is going to be a really weird diagram. In fact, I think this is going to be a terrible diagram, but this is fine. So what we want to do is we want to this is quite weird. But this is interesting, I think. Yeah. The design of this problem is kind of cool. Also good that they're all at least 3, because a chain of length 2 would be totally useless. So this vertex is part of the tree. We have the root. Now we like stick a chain onto the tree. And in doing so, we invalidate both of these vertices. So we can't connect anything else to this. And we want to have the tree have at least k white. And then we can do the same thing. Actually, why am I using blue? Whatever. We want to have at least k white. And then we can do the same thing sort of here. And we can do the same thing sort of here. So everything adds, every chain we stick on adds more white vertices. Specifically, if we have a chain of length L, then it adds L minus 2. Minus 2 because one of the vertices on the chain becomes invalidated, and the other vertex that we attach it to becomes invalidated. So we lose 2, but we gain the full L from the chain. So that's the upper bound on the number of white vertices we can have, meaning that like first we can check this and then check for like building a tree with at least k white vertices. That part's simple. The hard part would be the minimum value of the tree, I suppose. The question is, how would you do this? Is this easy? People are solving this. Okay. People are indeed solving this. Interesting. We've got like this very close tie, even though we're not that. Or because I have one of the worst penalties for this. People are solving F. Okay. So anyway, so my guess, it seems like, okay, I'm not gonna say my guess, but it seems like the optimal thing to do is to connect the chain in the middle, because that makes every other vertex like as high as it can be. Like you have two vertices of depth 1 from it, and then you have two vertices of depth 2, and etc. Or like depth, this depth plus 1 plus 2, etc. So now something interesting to try is binary search, because we definitely can't just simulate. I think the naive thing to do would be to simulate putting the chains on. Like we put the biggest chain as high as possible, and then the next biggest chain as high as possible, and so on. And so we do sort of like Dial's algorithm or something weird, but that's not possible because like, k, 10 to the 9th. But maybe we can do some sort of binary search. And so how would this work? Is this even possible? So adding a chain kills one white vertex. It adds two white. It adds at most, or it adds two white vertices of distance of that plus 2. At most 2 of that plus 3. At most 2 of that plus 4, etc. Even odd chains are kind of separate. And we want to see if it's possible to do things. And so we want to see if we can have at least k white vertices of a certain distance away. Is there some way to check that? Well, the distances aren't going to be that bad, I guess. We can do some wacky prefix sums or something. Maybe we just can do some wacky prefix sums. Okay, so it should always be better to have the longer chains be as high up as possible, because that gives you more space that's closer. Because if you like swap two chains, then like you get fewer good vertices, kind of. I think like exchange arguments means I think you can do some sort of exchange arguments to show that you want the biggest chains first, and then now we do some sort of wacky prefix sums. I guess that should work. Don't see why not. And a lot of people are solving this, so it doesn't seem that bad. let's see, n to k. Okay, how do I scroll? I guess I'll use the mouse to scroll. So basically the idea is when we stick on a chain of length x at depth d, then we get two vertices at d plus 2. We get -1. We get -1 at depth d. Nothing changes in d plus 1. We get +2 in d plus 2, +2 in d plus 3, +2 in d plus 4, etc. until we get to d plus like x over 2 or something. And at that point, we do some casework based on even or odd. But the point is, like, all of these are going to be +2 because we stick the chain in the middle. Because if not, then everything's just lower and it's worse. So we don't want that. We want to stick the chain in the middle. So we get +2 here. We maybe get a +1 here, but that's not that big a deal. Because another thing we utilize is that there are at most O of n chains, which means that like we're only interested in at most O of n different values of depth to stick the chains on, which means we can do this sort of weird prefix sums. And so it just comes down to binary search. Okay, that should work. Yeah. So L equals 0, R is equal to 26 should work. It's not gonna have to be nearly that big, but it should be fine anyway. Let's see. So LL. Oh, we don't have tests. Nice. Some. Do I need a prefix somewhere? Yeah, I do. Prefix sums of size 1,000,000. Technically, we don't need to do memset for the whole thing, but that's not that big a deal anyway. Because it'll take that much memory in the end, and memset's quick anyway. So LM equals L plus R over 2. So if possible, try for lower. Otherwise, go higher. And the answer should just be L. So now we do some stuff. So LL cur is equal to 0. Actually, it should be 1. This is the current number of vertices we have because sometimes it's suboptimal to stick on chains at all. So we want to check at every possible step if we have at least k. And again, I will explain this more in depth later. I just want to AK this because I've never AK'd an edgegram before, and it's cool. So plus p sum 0 minus p sum 1. This technically doesn't need to go up to equal to, but that's fine. It's not that big a deal. So let's see. While let's say r plus equals p sum I, tot plus equals r. While total is greater than 0, we take as many as we can. Actually, this should initially be 0. And we're seeing at any point if it's possible. So while total is greater than 0, let's see. Oh, wait. I knew I would screw my own variables over at some point. So while total is greater than 0, we consider taking the current thing. So minus minus curvy, because we're not using that. Minus minus tot. And we say we're going to take the pointh curve, the pointh curve, yeah, or pointh maybe. So I'll pause is equal to I plus 2. That's the start of what we're adding. And then our pause is equal to I plus 2 plus the floor of a point minus 1 over 2. That should be how long the chain lasts, right? Let's see, because if we have, like, for example, plus 3, then we have something like, using the mouse again, just to quickly illustrate something. So this is 3 minus 1 over 2 is equal to 1. And we get, like, wait, how would this work? I guess our pause is exclusive. Because, like, this is the thing from the tree we're killing. This is depth D. This is D plus 1. This is D plus 2. So we start gaining things at D plus 2, and we stop at D plus 2 plus this. So I'm going to make that inclusive. If L pause is less than or equal to M, curvy plus equals min R pause M minus L pause plus 1. This is basically just adding the number we get. And so it's the minimum of these because it just is. Like, either we run out of things from the chain or we run out of things that are less than or equal to M. Then, and of course this is only if L pause itself is within range. Then plus plus, or p sum L pause plus equals 2, p sum R pause plus 1 minus equals 2. That will do the interval that we want. Then if a point, also eventually plus plus point, actually this should be within this loop. If a point is even, then we get an extra position at p equals R pause plus 1. Then if p is less than or equal to M, plus plus curve V, plus p sum p, minus minus p sum p plus 1. And that should be it, I believe. If curve V is greater than or equal to k, pause equal 1. That is, we found an answer. Okay, let's verify everything. That should be it, though. So read in n and k, read in the array values, sort reverse, do binary search, then memset on the prefix sum array, set it all to 0. Start with a value at 0, which is the root. Then we say r plus equals p sum I, tot plus equals r. That's just handling the prefix sums. Then while we have something at this location, I think we can do tot equals r, yeah. That's just the number at this location. Yeah. So if point is out of range, we have no more chains we can do. Otherwise, decrease in the current because we're getting rid of something, decrease in the total because we just used it. Then we say, we start at I plus 2, and then we end at like the end, which is like the depth of the chain, excluding the last point if it's even, and then that minus 1 over 2, right? So if we have like 4, for example, if we have a chain of length 5, then we'll get 2 more. So we'll have 4 over 2, 5 minus 1, 4 over 2, 2 minus 1, 1, which means that it's going to span from d plus 2 to d plus 3, which is what we want. If this is valid, then we take this, do the prefix sums. If it's even, we have an extra thing to consider, specifically at the end of this position. And then we advance point because now we have a new chain to work with, and we continue. So if curvy is greater than or equal to k, pos equals 1, which is check everything. 3, 4. If LV is equal to right. What happened? Okay. Try submitting, I suppose. Just went over everything. Everything looks good. Bounds are fine. A million is way overshooting it. A million, 1.5 million is definitely like overshooting the overshooting. Okay, that does it. We have AK'd this edurand. That is very nice. The people getting wrong answers. Or TLE, nice. Oh, anyway, currently in 18th. That is pretty good. I imagine my rank will drop again because I have like a quite decent penalty, but that's totally fine. Yeah, I'm like one of the worst to have all 6 problems, but that's totally fine. Actually would have won this round if it was unofficial. Or actually, maybe not. Maybe one of the other guys would have come from the shadows, like some of the other people who were official. Yes, yeah. As I said that right there. All right. So if not for the writing tablet, we would have won. But that's fine. That's fine. That's fine. Totally happy with this. 20th, rapidly decreasing 20th is still great. Who just got ahead? Who made their submission? Is someone doing it backwards or something? Okay, well, anyway, again, that's not that relevant. No. Cool. So, let me attempt explanations. Yeah, let's see. Okay. At this moment in time, I'm just taking note of this so I can maybe use this for the thumbnail or something. At 1:30:56. And hopefully I don't get hacked. Actually, is there anything that could be hacked? Let's see. So this is just like do the casework. This one would be fine. I handled my edge case. This one would be also fine, I would suppose. Because, I mean, I imagine they handle the off by 1 errors in the tests. This one would be fine. I guess I could stress test D. This one is totally fine. And this one is basically just this, like, I can't imagine, it'd be hard to, like, hack it, I would guess. Yeah, so that's fine. All fine, all good. Actually, in the meantime, I'll stress test D. Why not? So I'll just like, the reason I had the structure be so it was like this run thing would be so I can do this later. For LLI equals 1. If I mod 10,000 equal to 0. So bool if ops.size is greater than n plus 5, return false. So the conditions were that it can't be more than n plus 5, and it has to be that. If not run I cout failed I and L and break. It's waiting for a test case number. What? Oh, 3. Right? Yeah. Okay, so we'll let that run. In the meantime, I'll start explaining things. So, A asks, alright, for the purposes of quality solutions, I'm going to use the mouse here. Unless there's something that totally warrants the writing tablet, just because I don't want to like make this be as terrible. But I'm going to keep using the writing tablet during the screencast itself. So basically, you're given a string consisting of either question marks, left parens, or right parens. However, there's exactly one left parens and exactly one right parens. And so the question is, can you fill the question marks in with right or left parens so that it forms a balanced bracket sequence, and or a regular bracket sequence? And the way to classify a regular bracket sequence is like, essentially it like forms an arithmetic expression. That is, you can like stick, you can make some, for example, like 1 plus 1 plus 1 plus 1 plus 1 plus 1, something like that, for example. And then the parens would just work. Another way to think about it is that if you consider the prefix sums of left and right, where like left is +1 and right is -1, then all of these prefix sums must be greater than or equal to 0, and the whole thing must sum to 0. You have to have the same number of right and left. Anyway, this is a common definition. I'm not going to delve too far into it now. But the problem is you want to find out if you can make a regular bracket sequence by filling in the question marks with left or right parens. So the first condition is that the number of parens must be the same, which means you have to have x left and x right, which means 2x total. And because x is an integer, that means the length of the string has to be even. So it's 2e5. Oh, I didn't even test that. Okay. That's fine. Can't imagine it would be a problem though, because yeah. So 2x, which means that the length of the string has to be even. So the first condition is that length must be even. And the second condition is that, well, okay, so consider like the strings like this. If we have some character here, like this right character, there's nothing, another interpretation of regular is that every left must match with a right. So nothing can ever match with this right because there would have to be some left paren to the left of this, but that's not possible because this is the beginning of the string. So if we have something on the end, if we have the right facing one on the left end, then it's not possible. And like the same for if the left facing one is on the right end. So no, like we can't have either this sort of thing or this sort of thing. And otherwise it's always possible. Here's why. Because say we have some sort of like, say these are not together, then we can pair this right one with this, and then we can pair this left one with something here. And then maybe we have some other characters in between, but we know that we have an even number of characters, and therefore it's sort of like the strings we filled in to match with the input characters are like totally separate from the rest. So we have these other characters and we just want to form a balanced bracket sequence, and the easiest way to do that is to do something like this. Like we can just put this down and this down and this down and this down, and everything will match with exactly one other one. Wait, why? Oh, I didn't compile it. Nice. And everything will match with exactly one of these. So essentially, we fill in the rest of the characters with these, and this is going to be balanced. So therefore, if both of these are satisfied, if it's even and we have a match for the input characters, then we're good. And that's the only condition. So we just check that. You can just check if the last character is an open parens and so on. Okay, red and blue. So we have some array. We have some values that we know are red. For example, 2, -5, and 7. And we have some values that we know are blue. And we have some values that we know are red, such as 3, 9, and 6. And actually, let's modify this a bit. Make this. Oh, come on! What is that? It's like a phone being loud. Okay, so right. So we have some things that we know are red and some things that we know are blue. We know in the original array exactly this many elements were red, and these were the red elements, and this many elements were blue. And we also know that the elements were in this order, which means like we can't have the red 9 be ahead of the red 6 because that breaks the order. So what we want to do is we want to fill in the array with these red and blue values, like however we want. But we want to do it in such a way such that the maximum of any of the prefix sums, and the prefix sum is just the sum of the first like x elements for some x. So like the first element or the first 2 elements or the first 3 elements or the first 4 elements or etc. We want to create the biggest possible prefix sum of any length, as long as it's like the maximum value. Yeah, we want to create the maximum possible prefix sum. So the way to do that would be as follows. since we're going to take some first x elements of the array, and we know that the red and blue elements are ordered, there are going to be some like values y and z, so that we take the first y red elements and the first z red elements, or blue elements. Because say we take some element that's like not of the first z, then if we didn't take this one, because we're taking a prefix, that would mean like we're not actually taking a prefix. That some element in the array will be left out, but it has to be a prefix, so that's not possible. So if we take some element of red or blue, we also have to take all elements before it, meaning that everything we're ever going to take is going to be a prefix of some prefix of the red array and some prefix of the blue array. And note that the length we have doesn't matter, which means that it can be any prefix of the red array plus any prefix of the blue array. So values are 100. Let's just try all prefixes. Like you can take the maximum red prefix and the maximum blue prefix and sum them together. You can also like brute force it, like try all red prefixes and pair them with all blue prefixes, which is what I did for some reason, and then like take the best of those. And so on. And so literally just try all red prefixes and pair them with all blue prefixes and take the maximum. Because we know that the answer has to be the sum of some prefix of red and some prefix of blue. And the mistake I made was that I didn't try taking nothing of red and some prefix of blue. So you should handle that. And the easiest way to do that is to not do brute force and instead just take the best prefix of red, the best prefix of blue, and add them together. That's the easiest thing to do. Then that's just O of n plus m. Or you can do O of n, m, or really however you want. It's not that big a deal. Because the constraints are small enough for it not to matter. You just want the best pair of prefixes. Anyway, I've not been hacked, right? Should be able to go a little bit without being hacked. Okay. Wow, this is like very close. Yeah. So that's a thing. It's indeed a thing. Alright. Wait, how did that work? Yeah, it was much slower on the earlier ones, and then faster on the later ones, but that ended up not making a difference, which is sad. Did I mess up on B? Alright. Right, okay. So for C, we have some weird constraints for building a fence. That is, we have something like this. We have this like ground level. It's too big. Come on. And then this here. And then this, and then this. And I'm going to move all these down. And basically we want to build these like intervals of length k. So that this is k, and that like some other things too. For example, like this, and then like this, and like this, and like this, and like this. And these intervals have to, and these are all length k, and they all have to satisfy the following constraints: that the endpoints of the fence must be the same height as the ground, or the respective ground on their levels. The middle points must be at most distance k minus 1 away, like from the respective ground levels. And also all like neighboring pairs of the fence have to sort of like touch. Their intersection has to be non-empty. So like for example, something like this would be invalid, or even something like this, where they touch but their intersection is like 0, so nothing happens. It's not valid. It has to be like, there has to be like at least one unit that they share in common, kind of. That's how they define it. And so we want to see if it's possible to build such a fence or not. We don't actually have to construct the fence, which is nice, because that would be annoying. So the question is, how do we do this? And the answer is what we want to do is we want to basically every level gives us an interval of the place where we can place the fence. So for example, call this like A1, A2, because we have an array of heights. Can't draw it all. Again, I'm only still using the mouse because I'm not used to the writing tablet yet. So like, for example, this interval is A1, comma A1. This interval is A1, A2, and then A2 plus K minus 1, because we can build it up to that high. And this interval is A3, A3 plus K minus 1, etc. And this is A6, A6, because we have the special constraint of the end as well. So actually, they should all be open intervals, but I don't want to re-bracket them. So you can assume these are open intervals and that they're inclusive of the ends. But the point is, like, we have an interval of places where we can place this. But, like, we also have an interval that's given to us by the fact that they have to intersect. So the idea is, consider, like, say this location is fixed, for example. Say, like, the previous block has to be here. Now, where can we place the block here so that it intersects with this? Well, it can be anywhere from the point where it like the topmost point where it still intersects and the bottommost point where it still intersects. And yeah, and so if this has a possible range, like if this has some interval, like it can be built anywhere from here to here, then it's still the same thing, but it's sort of like more lax, that we can build it anywhere so that like the topmost point where it still intersects the topmost red thing, and the bottommost point where it still intersects the bottommost red thing. And so this is simply the lower bound of red. Like let the red interval be L and R. Then the blue interval would be L minus K minus 1, because like this has to be 1, but this is length K in total. So then like the freedom we get is sort of K minus 1. And I'm like finding the interval for the bottom just for like convenience. And we have the same argument here that this would be R plus K minus 1, because this is 1. So we get sort of K minus 1 freedom up top as well. And so based on only the interval of the previous like fence post or something, this is what we have to do to make it so it intersects. I'll make this capital L. Yeah, so that's the interval we get from the previous one. And we also get some interval based on the ground constraints. So we can basically like just intersect these intervals. And the way to intersect two intervals like A, B, intersection C and D, the easiest way is to make a new interval with the maximum of A and C and the minimum of B and D. And the reason this works is just like draw two intervals out. Their intersection is going to be here. And it's basically going to be the maximum of the left coordinates and the minimum of the right coordinates. So like this, you can verify that this works for all cases. Like for example, here the intersection would be exactly this red thing, which I drew badly. And also, for example, here, this intersection would be nothing, which means that the minimum x coordinate would be greater, or the maximum small coordinate would be greater than the minimum x coordinate, which means we get this like degenerate interval. But the point is that we're just intersecting two intervals. The interval given to us by the first constraint, that we have to like build it within a certain height from the ground, and the second constraint that they have to intersect. So we find the interval for the first one based on only itself. We find the interval for the second one based on the previous one and its own constraint. We find the interval for the third one based on the previous one and its own constraint, and each time we just intersect it a bunch of times. So that basically works. But again, we expand it out a bit every time because of the way that we're allowed to intersect. So if the previous interval is LR, the final interval we get is like LR with the intersection of AI or HI, whatever you want to call it, and AI plus K minus 1. Because again, that's just the other constraint we have. And this is the intersection symbol. So when we intersect all these intervals together, we get our final answer. And if our interval is ever degenerate, like down here, where the left point is greater than the right point, then we know it's not possible. And so we can just check that at every step. Right, okay. This one's kind of cool, and kind of also like not cool, but also cool. So let's just say it's cool. I don't know. Actually, yeah, I'll say it's cool. It's kind of like a neat trick. So we have a bunch of we have an array where every value is initially equal to its position. That is, we have like the identity permutation, like 1 to n, where every element is I. What we can do is we can pick two indices. We can say this is the first index and the second index. Then we can set this element to be the ceiling division of this value and this value. So like this value would become this value 6 divided by this value 4, and then the ceiling of that division, that is just rounded up, which becomes 2. And then we set this value to that, and the other value is unaffected. We want to do some operations with this array, and we want to do some operations with this array so that like the final array should have n minus 1 ones and 1 2. So it should be like, for example, 1 2 1 1 1 1 1, or just anything of the sort. 1 1 2, you know, anything. That's our final goal, and we have at most n plus 5 operations. Now 5 should stand out as being weird, because like first of all, it's not log, and that's weird, isn't it? Like usually we do something with log, but it's not that easy. So what can we do instead? One strategy, well, actually, when trying to think of strategies, the problem we end up running into is that this element is too big. Like, what can we do with this element? Because if we take two elements x and y, where x is less than y, then the ceiling division is going to be equal to 1, or x is less than or equal to y. If we have x greater than or equal to, or if we have x being greater than y, then the ceiling division is going to be 2, or at least 2. Which means like we can't do some sort of simple cheeky strategy where we just like divide everything by the element bigger than it. Like, for example, this can become 1 if we do it with 7. This can become 1. This can become 1, sure. But then what do we do with 7? The problem is that it's still huge, and if we make everything else 1, there's nothing we can do. Because 1s are totally useless. Like, it doesn't, like, the division of something by 1 is itself. So it's totally useless. And dividing 1 by something else just gives you 1. So when we have a 1, we're done with an element. But say we did have some like log factor, like n plus log n or something. Say we had that many operations. Then something we can do is like we can kill like we can kill the last half of the array using 7. For example, like this. And then once we get to like the first half of the array, what we can do is we can ceiling divide 7 by 2. And what that does is it's going to have the value of the largest element. which means that it's still going to be the largest element. So we can continue doing the same thing with this half of the array, but at the same time, it's smaller. So when we eventually get to the beginning of the array, we're going to have divided this by 2 a ton of times, 7 to 4 to 2, and then we would have it be 2. And then we can, for example, pair it with this 2 and make one of them 1. So that's like a possibility. But the problem is it takes log operations, so we can't do that. But why are we constraining ourselves to dividing by 2? What if we divide it by a bigger element? The only thing we really care about is that this element remains the biggest. Actually, it doesn't even have to remain the biggest. We want the biggest to decrease by as much as possible, while also making it so the biggest isn't too big. So instead of 2, let's fix some value k. And again, this doesn't work because we don't have log operations, or a log extra operations. So let's pick some value k. What we want is that the current biggest value, so for example 7, divided by k, the ceiling division, is at least as big as k. Say we didn't have the ceiling division, then messing with the equation a bit, we get that k is equal to square root 7. Right? So the best we can do while still maintaining the property that we have a biggest element that's not too big is we can take the square root of this number. Yeah, so what is that? So we can take the square root of this number essentially. And so once we sort of kill off the first few elements, make them all 1s, then we can turn this into, for example, a 3 by making it 3. And then now we have k equals, and then now we have the biggest element is square root n or something. And then we continue doing it for this until we get to the next value of k, which would be the square root of the square root of 7. So then we get a value that's like the square root of the square root of n. And then we do it again with this new value, and then we keep taking iterative square roots. And so the number of operations we use is the number of times this takes to converge. Like the number of square roots we need to do before n becomes 1. And, well, let's just test that. We have 2e5. So square root 2e5. Let's do 1. Let's do it again. Square root of 2e5. Let's do it again. Square root of square root. Do it again. And do it again. Look at that. 5 square roots. N plus 5. How interesting is that? Now that seems intended, doesn't it? I'm actually not sure if it's intended, but that works. And any number will converge within 5 steps, I believe. 4 or 5 or 6. It doesn't matter exactly, because notice that we save an operation because we don't have to touch this one, and we save an operation because we don't have to touch this one. So it's n minus 2 plus 5 or something, so it's n plus 3 or something. It could be n plus 4 also, but the point is it's totally comfortably within the safe zone, within the number of operations. So we're it's totally fine. How did we do? 28th. Okay, that's pretty good. Could have had a not so bad penalty, but it's still pretty good. Yeah, okay, anyway. So that's the idea. So I get rid of as many scribbles as I can. That's fine. So we pick some value k. We pick some value k such that n over k is greater than or equal to k, which means that k is around square root n. So then we divide by that, and then we get n over square root n, which of course just becomes square root n. And then so like doing this analysis is only necessary to prove the solution. We don't even have to like compute k. All we really need to do is just like go through and find the first value of the array that satisfies this. And then when we do that, we divide this by that value of the array. And then we continue like killing elements like nothing happened. Then we end up killing this one anyway. And then we just keep going. Or actually, we don't kill that one. Then we just keep going. And then when we get to this first 2, we can just say that this is the 2 we want. And then we can divide this by this 2 until we're done. And because of like the same square root analysis, like it's still going to work out. So in terms of implementation, it may help to like define a specific function that does this for you, that does an operation. And then this is the only condition we have to check. And if so, then we divide the biggest number by this element. If the ceiling of this divided by AI is greater than it, then do the operation. Okay, we have 2 more problems, which would sum up to all of the problems, which is nice. And the idea is we have this binary string. For example, let's take 0, 1, 1, 0. And let's take some other string. And we have this string of length n, and we have this parameter k. So like something like this. Let's take some other string of length k. And basically we're going to compare this string to all substrings of the big string of length. Of all length k substrings of the big string. So for example, we compare this string to this one, and this one, and this one. And we call the small string beautiful if for every pairing we consider, at least one of the characters are the same in both of them. So for example, this 1, 1 is beautiful because this substring shares this character, these substrings share both of the characters, and these substrings share this character. And they say like a bit similar, meaning that we share at least one character. That's what they say for similarity. So then, basically we want to construct a string that's beautiful. That is, it's a bit similar to each of the substrings of length k. And if there exists such a string, we want to construct the lexicographically minimal one. Since that's defined, and this is E, I trust you guys to know what that is. So yeah, how do we do this? The first observation is like, actually basically the only observation is that like, consider some string of length k. What doesn't match with this? Or rather, what does? Like, consider the exact complement of this string. That is, we have 0 and 1. So, therefore, these strings are not similar because we define this string to be the string where every bit differs from the other one. Right? So, this string is not a bit similar. But what about other strings? Like, any other string that's not equal to this differs from this string by at least one character. So for example, we could have 1, 1, or 0, 0, or 1, 0. But it differs by at least one character. But we know that every single one of these characters is different, which means that anything that's like, any character that's like not the same as this is going to be the same as this because like we only have 2 possible characters. Which means every other string that's different from this by at least one character will be equal to this string at that character. For example, like this. Because this is different from this one, it's therefore the same as this one. So what I'm saying is every string that isn't the complement is going to be similar. A separate way of thinking about this is that this substring of length 2 invalidates exactly one possible candidate string. specifically the exact complement. So this one will invalidate this. This one will invalidate this one. And this one will invalidate the complement of that, which is this. Because again, everything that isn't the complement differs from the complement by at least one character, and that means that it's the same in those characters that it differs by. So what that means is that there are only at most, the number of invalid strings is just the number of intervals of length k, which is like n minus k plus 1 or something. No, yes, n minus k plus 1. Which means, say we just tried all strings in lexicographic order. Like say we tried, for example, 0, 0, then 0, 1, then 1, 0, then 1, 1. We would find a match quickly. We would find a match in at most n minus k plus 1 iterations, because only this many strings are invalid. It's like pigeonhole principle. By pigeonhole principle, at least one of these strings must be valid, or like something. Maybe it's not pigeonhole principle, but it's like that same idea. At least one of these strings must be valid. And of course, this is O of n times the time to check. So now, if we could find some way to check some string quickly, like we can say like, if we could ask, is this string invalid quickly, then we'd be done very quickly, because we only need O of n strings to check. One way to do this is with simply hashing, and that's one way to do it. And in fact, you can do a simple polynomial rolling hash that works, and you can do it like that. But there's another way to do it that makes it like fully deterministic. And the way to do that is to notice something else. Like, consider that we're going through all lexicographic strings, right? So say we have like strings of 500 characters. But by the time we go through 10 to the 6th of them, which is going to be like O of n, like not many of the characters are going to be different. Only the last like log base 2 of 10 to the 6 characters are going to be different from the initial string of all zeros. Just because that's how binary works. Like, it's like the length of 10 to the 6th in binary, because we're just iterating through all binary numbers of length 500. And so 10 to the 6th would be the 10 to the 6th number in binary. And that doesn't have that many bits, meaning that everything that's like irrelevant. Okay, 1 second. My parents are calling. I should handle that, I guess. Okay, never mind. It said scam likely, so I guess that's irrelevant. But the point is, like, if we write 10 to the 6th in binary, like, it's going to be the 10 to the 6th binary number. Meaning that, like, everything that's not related to 10 to the 6th isn't going to change, because we're only, like, interested in the bits that are involved in 10 to the 6th. And this is the number of bits we have. Meaning that, when we're looking for strings to invalidate, like, kind of by the same argument, we don't really care about that many characters. The only characters we care about are the characters that would be involved with these bits. Specifically like the last few bits. And so log 2 10 to the 6 is around 20. And so I picked a value like 22. And so it means you only have to care about this. You only have to care about the last, for example, 22 bits. Because everything else won't matter, because we'll find a match by the time that we get to wanting to modify anything that isn't the last 22 bits. Like, we'll find a match before then, because the last 22 bits covers 2 to the 22 numbers, which is like 4 million. Which means that we'll definitely find a match before we get to modifying any of these bits. So the only bits we care about are the last 22 bits. And therefore, for every substring of length k, we only really care about the last, it's the minimum of k and 22 bits. Because k might be tiny, in which case we don't have that many strings that we could check. But yeah. So the idea is we only need to care about that many bits. And so notice that like already we've been talking about this. This just maps to a number. So we can just store like a huge visited array that basically says, have we visited each number or not from 0 to 2 to the 22 minus 1 or something. And then at the end, we can just like iterate through this and find the first number that wasn't visited. The only problem is handling the multitests. But a trick that I like to use is using like a timestamp array. So basically, like, we want to ask, say we're in like test case 7, for example, and we want to ask, has this value been visited in the 7th test case? So instead of using booleans for a visited array, we store the last test case that it was visited in. For example, if this is never visited, it's like -1. If this was last visited in the previous test case, this would be 6, and this could be like 3 or something. And the point is, like, the reason this works is because now we don't have to update these values every time. We don't have to set them to 0. All we do is we check if we know some value was visited in the test case if it's like its timestamp is specifically this test case. So only this one will be visited because all the other ones don't matter. And so the cool thing about that is that we don't have to reset. We don't have to reset because when we get to a new test case, everything will automatically default to 0 since it's not equal to this value. So it's like a trick you can use to make it so you can use a huge visited array without having to reset it. And that's what I'm doing here. So yeah, that works. Basically only care about the last 22 characters, and you can just try all possible strings until you find something that match. And of course, if k is small, like something like 3, then you'd only check up to the numbers that you can actually make with k characters. So it would be the minimum of k and 22 or something. Anyway, for the last one, this one's fun. You have a bunch of chains, and you have this root. Let's say you have this root. I'm going to use red as white and blue as black. Just like the white they use in the problem. Okay, so basically you have a white root, and you have a bunch of chains, all of which are initially white. Chains are just like paths. So for example, something like this, something like this, and something like this. And so the idea is you want to construct a tree from these chains. So a thing you can do is you can draw an edge between 2 white vertices, and again, the root and every vertex in the chains are initially white. So like, for example, I can draw this edge. And then what drawing this edge does is it makes it so both of these vertices become black. And so you can only draw an edge between 2 white vertices. Black vertices are unusable. And now, for example, if I wanted to extend the tree further, I could draw this edge, and then these would become black or blue, or however you want to call it. And then I could draw this edge to extend the tree further. And also, since it has to be a tree, you can't like draw 2 vertices between 2 chains that are already on the tree. That would be pointless. And so, more constraints. Each chain can only be used once. We can't use like the chain of length 4 multiple times. And you don't have to use all the chains. So, the question is, now we have some parameter k, where k is at most 10 to the 9th, which is a big number. And we ask one thing. First, we ask two things, kind of. First, can we construct a tree with at least k vertices? Or can we construct a tree with at least k white vertices? And if so, consider like the kth highest. Consider the kth highest node. What's the minimum depth we can make for the kth highest node? Or the kth closest white vertex to the root? Right. So let's observe some properties about this problem. First, how do we attach the chains? So we want these chains to be as close as possible to the root. So the first step is establishing that we want to attach the chains as close to the middle as possible. Like we would want to do this in the middle rather than at the end. Because say we do it in the middle, then we get like 2 vertices of depth 1 away. We get like, and then here we get like 1 vertex of depth 2. But here, for example, we would get 1 vertex of depth 1, 1 vertex of depth 2, and 1 vertex of depth 3, which means that like all the vertices go deeper. It just gets worse the farther you get from the middle, which means we always want to attach chains in the middle. And the second step is that you always want to use the larger chains first, or like higher. The larger chains want to be higher up. And we can show this by exchange argument, kind of. Like say we have a chain of length 5 and a chain of length 3. Then consider what we would do. Like for example, using 5 first and then 3, we would do this, and then we can do something like this. So we get 1 vertex of depth 2, 2 of depth 3, and 2 of depth 4. But if we do it the other way, then like it means that because the chain of length 5 is bigger, it means that more vertices are going to be lower, and less vertices are going to be higher because we attach the chain with fewer vertices higher. That's kind of like the intuitive explanation, that more vertices are going to be lower when we use bigger chains later. And less vertices are going to be higher, which is bad. And so doing the counting, we get 2 vertices at depth 2, 2 vertices at depth, or wait, no, 1 vertex at depth 2, 2 vertices at depth 4, and 2 vertices at depth 5. Like it just gets worse the farther you go down. This is not a proof, it's just sort of in like a visual explanation. That, again, if you use a higher chain earlier, then you'll have more vertices that are higher up as opposed to using it lower, where all of the vertices will be attached relative to a lower depth. Like relative to the starting vertex, they'll be lower. Or relative to the root, like their anchor vertex will be lower, which means that all of the other vertices will also be lower. So first, we attach chains by the center. Second, we attach the largest chains first. Now, this just gives us like a process for attaching the chains. If the constraints weren't so big, at this point now we can just simulate it. And we can just like straight up construct the entire tree. And yeah. Also, we want a way to check like, what if we don't use all the chains? Because that may also be optimal. Like, for example, in test 2, the best thing to do is to not use all the chains. Oh, and also the third thing is that we want to attach new chains as high up as possible. Because if we don't, then we would be in a position where there's no reason to attach that chain anyway. So these 3 things being said, notice that if we have this many vertices at least k away, or if we have this many vertices exactly k away, or at most k away, then we have more than that many vertices that are more than that away. Like for example, if we have this many at position 1, this 2 at depth 2, and 1 at depth 3, then if k equals 3, for example, then we have more than k the farther we get away. And the closer we get, the fewer vertices we have. What I'm sort of implying is that we can binary search on the answer. So we do binary search. And with the binary search, because we have a way of an ordering to place the chains, it's sort of just simulation. All of the depths are going to be at most, because we construct the chains as high up as possible, adding a new chain adds like at most like 2 depth to the new chain we add, which means that it's going to be like O of 2 times n is going to be the lowest depth we ever use. So we don't use that many depths, which means we can sort of simulate it using some sort of prefix sums, basically. Like, if we have a chain of length 8, and then we attach it to the root, for example, then it means we lose the vertex at the root, so we get -1 at the root. Nothing changes at depth 1. Actually, let me illustrate this. So we have this root here, then we attach this chain of length 8, for example here, and here, and then we do this here. So we initially had this vertex here, but now we lose it, meaning that we lose the vertex at depth 0. We gain 2 at depth 2. Nothing happens at depth 1. At depths 3 and 4, we also gain 2. And at depth 5, because we have an even length chain, we gain an additional 1. And so the point is, like, we have a bunch of 2s, and then we have like a single 1 maybe at the end. But we can do all this, like, this is just asking us to add 2 on an interval, basically. So you can do this with anything, like some sort of segment tree or running prefix sums or things. The simulation isn't really the hard part. I guess the hard part is figuring out how to do things. But once you have the simulation, then you basically just do some sort of prefix sums along with the binary search, and you can do math to figure out exactly how it affects the array, and check at each step whether you have at least k vertices of the current depth that you're solving for or not. And if so, then it's possible, and if not, then it's not. And yeah, just normal binary search from there. So yeah, that basically does it. So we find an ordering for the chains. That is, first, we know we want to attach them at the middle. Then second, we know we want to attach the largest ones first. And third, we want to attach them as high as possible. Because if we don't attach them as high as possible, then like, why do we attach the chain at all? Because the point is the chain gives us more vertices that are like within the depth. But if we attach it lower, then like we're attaching it at a point that would be below the depth anyway. So all of the chain would be useless because it would also be below the depth. Like the only reason we wouldn't want to, like say we're solving for like this depth here, for example. And all of these are white. All of these are valid. Then the only reason we would attach it like here instead of here will be because this is valid and we don't want to like lose it. But then when we attach this chain, it's going to be pointless anyway because everything's going to be below the depth. So there's no reason to do it this low. And there's no reason to do it lower because no matter what, we're losing a vertex above the depth anyway. So we might as well do it as high as possible. That's kind of the argument for that. And then we binary search. Yeah, that's it. That's basically all it is. Have there been hacks? Hack on E. It's probably hashing, I guess. Someone tried to hack me with invalid input. Nice. Okay. Suppose that does it. Cool. Yeah, so yeah, fully solved everything. I have nothing to say. This was quite cool. I liked E. I'm not sure about F. It seems sort of just like bashing things out. Do is a cool thing. I haven't seen square root that often used like that. Yeah, it was fine. Alright, let's see. In terms of future rounds, I might do the goodbye round. Not sure. We'll see. Depends on certain things going right or going wrong. Yeah, we'll see. But anyway, to all of you, goodbye.